Okay, so today we are going to talk about questions about the interrupts. And so interrupts is actually, it was a pretty long lecture and it was split over two classes. And so we went through what you already know about interrupts, what's happening when an interrupt occurs at a high level. But then the rest of this lecture is about what's happening with interrupts at a lower level, right? When an interrupt is getting executed, and so who cares about these interrupts? Pretty much any kind of system that is trying to run at a high performance, and that's you join Google, you join Facebook, everything is about latency, and interrupts are really the one of the major bottlenecks regarding latency. So let's have a couple of questions, and then we can get started with that. So you can speak your questions, you can type them in the chat, and then we'll go through them one by one.
Can I ask one real quick?
Yeah.
So I was wondering if there was ever ways you could only disable certain interrupts, like if you had a timer interrupt where you're counting the overflows in order to time something, is that something that you would still want to happen during an atomic operation because it would like mess up the timer?
Okay. So can we disable select interrupts? Okay, so we can put that down. Let's see, someone else is knocking. Okay, other questions?
Can you go over what the watchdog does again?
Yeah.
And I think this might be covered in the second lecture. I'm not sure. But how do we deal with interrupts and concurrency in race conditions?
What do you mean by that?
So like accessing, I guess it doesn't matter because the interrupt, nothing else is working at the same time. But like what if, does the interrupts like change the deal with like concurrency?
Yeah. That's a good question. Actually, it's not necessarily the same as just the generic concurrency lecture that we had. Okay, other questions? And then if you want me to go over parts of the lecture, just let me know. You went over some of it, you didn't go some of it. You were like, yeah, I'll come back to this, or I'm confused about this. Okay, so when I took 380, I had to manually set up the interrupt vector table using assembly instructions and function pointers. Yeah. So, okay, so how are interrupts actually, set up and initialized? That's a great question. That's a great question because, we shouldn't be taking that for granted. Okay, we'll go over that too. And any other questions?
Yeah, the slides on like the interrupt recognition and acknowledgement hardware in the slides during the lecture were like rotated, so I couldn't see you talk about it, or when you were talking about it, it was like rotated sideways. So
Okay.
if you could like go over that, so you could like point to it as you're talking about it.
Yeah, so we'll talk about servicing interrupts with the flip-flops.
Yeah.
That's an important thing. Yeah, actually, that's not found in any kind of microcontroller textbook. Okay, so let's get started with this, and then you can feel free to interrupt at any time. Okay, so I think let's start with how do we set up interrupts right in the beginning, right? So if we were to go back to like our let's say if you want to go back to our lecture, let me see if I can find that from some old lecture where we have the architecture and assembly. Okay, So we want to know how our interrupts basically getting set up, right in the beginning. And so we know our main memory map that is there, right? So and our memory map has, you know, this kind of structure over here where we have these general purpose registers, right? And then if we go back to like an even earlier lecture, like from our timers, you know, like timers lecture, we basically looked at, you know, what is in this memory map, right? In terms of this interrupt vector table, right? And the question always was, well, okay, who set this up? How were they set up, and so on. Actually, maybe not in this lecture, but we'll find it in a. Let's see if it's in the. I'm just looking at for the main memory map, and so we have you know, a set of interrupts that are already pre-populated in that, right? So are you just trying to find the. So in okay, maybe I'll just talk through it first, and then so in this area, right, where we have our 32 general purpose registers. They're just generic places now that you can use for any purpose, for the basically for the CPU, for the ALU processing, for the data paths to actually get, you know, I mean, to store intermediate results. These 64 IO registers, right? And if you look at the top of this memory map, let me just give me a minute. Let me find the right, you know, image for the memory map, and then we can go through that. Let me see. It's not in this one. It's not in this one. Let's see if it's in stacks. Maybe it's in stacks.
We can't see the window you're currently on. We can only see the PowerPoint right now.
Okay, I see. Yeah, that's fine. That's fine. I'll share this with you. I'm just trying to find the memory map so that I can then show you where these interrupts are, right? So, okay, let me switch back to our lecture, and then we'll come back to this. Looks like. So in the beginning we have, you can see this slide, right, over here, the main slide. Can you guys see the lecture outline? Okay, great. Okay, so let's start with the first question now. With who sets up these interrupts? These interrupts are basically set up in the by Atmel, right? So Atmel has already set up the interrupt locations of, you know, where you have your ADC interrupts, where you have your timer interrupts, and that entire stack. I mean, that entire interrupt vector table is predetermined, right? So you're not like, unlike in your operating systems course where you are setting up like a specific interrupt. In the microcontroller, you just have the luxury of having your preset interrupts. Okay, so I think I will.
So in that case, for the microcontroller, like, okay, in the operating system on x86, I was able to, when a certain interrupt hit, let's say like a timer interrupt or something, I could go and set a function pointer, so it would go and jump to that function and run that function, and my operating system would go do something based off of that, like, I don't know, keyboard. For the microcontroller, are you not allowed to set which like function you want to go to when an interrupt hits, or does it go to only one place always? or can you change that location?
Yeah. So the question is, suppose I have like a particular interrupt here. Now, what is this interrupt on this table, right? This is at a particular address. We are assigning any action that is related to, say, this PC interrupt, right? So this is basically like a pin change interrupt. So we don't have to worry about what that means. It's basically like if you press a button and then there's a change in the signal, then that causes an interrupt from that pin change. So now the question is, now at each of these locations, right, that are kind of predetermined, these addresses are known, we have to specify, we are storing in that location the address of the interrupt service routine. Okay, so when you call like a timer interrupt over here, or an ADC interrupt, then that you're calling that interrupt function right over here, and essentially this interrupt function, the interrupt service routine, is the address of that interrupt service routine needs to be entered here. So whenever that interrupt actually occurs, then the program counter is going to go to that location. So now when you have your interrupt service routine here and you basically just instantiate that, now when your code gets compiled, the compiler looks at it and says, hey, this is the special compiler tag for an interrupt service routine. And then it goes and looks up in the interrupt vector table, which is this interrupt matching with, and that's just this int0 vector over here. And so this int0 vector is, if you go and look into the Atmel library that is included, it will provide the address of that, of 0002. And essentially, the compiler will go and write the address of where it is going to place this interrupt service routine. So there are two aspects to it, right? So you have basically a predetermined interrupt vector, and that's what is that's this at this address. So you can say, okay, well, I want to do something else at this address, and you could even try to reprogram that right over there, that when something happens, but when this something happens over here, it's going to go to that address automatically. So that is already baked into the circuitry, that if we have an external interrupt, that means I have a pin press, and that triggers this external interrupt from this particular pin, then it's going to call, this interrupt is going to go to this address. And then it's going to look up at this address, what is the address of the interrupt service routine, and then the program counter is going to jump to that location. So you already have the functionality of the reason for why this interrupt would be triggered. But what happens when the interrupt is triggered, that's up to you. So now, if the question is, well, I want to have and I want to trigger some interrupt in the middle of my code, and I want to basically say, whenever I trigger this interrupt, it should go to that location. So that specific, that's like a customized interrupt that you have. That's not supported with this microcontroller. That would be supported with most processors, where you define your own interrupt, and you add your interrupt. Basically, you would have like custom interrupt at this location, and then you can you can basically have your interrupt service. So you can customize the trigger for your interrupt, and you can customize what is done when that interrupt service routine is called. For the microcontroller, the trigger for the interrupt is already preset, and because that's much easier to sort of set up and have like a static sort of allocation of these interrupt vectors. So you do not have that facility of having a customized interrupt in this case. Was that part of the question?
Yeah, you perfectly answered that. I have a follow-up question, I guess, to that, which is, so in the process of when an interrupt happens, so it would only change the program counter, right? No other registers get changed unless within your ISR, changes it changes a register. Is that right?
So when an interrupt happens, then the program counter is jumping to that location, but you have to save the context of the program, right? So you have to save all your registers, you have to save everything that you're doing right now, your status register, you have to have a return address. It's just like calling a function. And that's what we cover, in this. So like we have this vector table here, and it's essentially just saying, okay, well, the program counter is going to, whenever the interrupt is called, the compiler basically is going to insert a function to say, go and look up what is at this address. So that has happened. So the lookup at that address and the interruption of what the program counter is doing to look up that address, that is done in this part of the code, in this part of the lecture, right? Or that's in this interrupt recognition, which we will come to. And that was Matt's question too. What's happening when this interrupt occurs? So when this interrupt occurs, we'll come to this in more detail. But this is actually saying that now we need to jump to this address. And so what the compiler then has to do is to say, well, if you're going to take this program counter and go to another address, then I need to save everything that we're doing right now so that you can go and service the interrupt. Then you have access to all the registers in the interrupt when you come, and then you need to have a return address to come back to the next instruction. And that will essentially allow you to sort of go from where you're executing instruction 1, instruction 2, instruction, and then just say during instruction 2, the interrupt occurs over here, right? So during instruction 2, there is an interrupt. So what the CPU does then is it says, okay, I know I have an interrupt waiting, and it's only going to check whether it has an interrupt waiting after the completion of the instruction. It does not actually jump to the interrupt in the middle of executing an instruction. And that's where, like last lecture's terminology of atomic, that this instruction is atomic, that's what is preserving this atomicity, that the lookup for, is there an interrupt waiting for me, that flag, that's a flag that the CPU will actually go and check, is only looked at the end of processing the instruction. After this, fetch, decode, execute cycle. After the execute cycle, it says, okay, I'm done with this instruction. Let me go and check what's the status, is there any interrupt waiting? If there's an interrupt waiting, then it basically goes and triggers, okay, we need to service this interrupt. And then the program counter has to switch to wherever that interrupt is. So say this code is running at line, 0003, and this interrupt is running at line like 9000. Then the program counter has to jump to 9000, finish that interrupt, but then it needs to know that it has to come back to, the address 0004. And so that is, so the return address and saving the registers, all of that is actually done by the compiler, because the compiler knows that here is an interrupt, we're going to service this. So this compiler again is an Atmel, GCC compiler, okay, and so this is a specific to Atmel, and therefore it does recognize, that now we are servicing an interrupt, and interrupt has been called right over there. So
would that be a callee save job? So the idea is like the compiler would say, okay, here's an ISR, and like you normally have a beginning of every sort of function that you have a bit of a callee save sort of job. Would it go and do that work except slightly modified because it's an interrupt? And then at the very end of the callee's function, at the very end of the ISR, it would go and then just restore all those values to be able to jump back to the original point you were in the mainline code?
Yeah. So pretty much it's going to be doing that, right? So it's just like you had your what you save onto the stack is saving everything onto the stack over here. Like a function is being called, is very similar to that. Now there is some difference. Okay, so let's look at how this actually executes, right? So if we look at, here, we have instruction 1, 2, 3, and then we have, we're executing instruction 4, and during that the interrupt occurs, and then the CPU then says, okay, well, I do have an interrupt after completing instruction 4, and then it says, okay, once instruction 4 is completed, it basically transitions the control to the interrupt service routine. So it loads the address, of the interrupt service routine to the program counter. The interrupt system is turned off, because we don't want to have, in this case, for this microcontroller, we don't want to have an interrupt occurring in the middle of servicing another interrupt over here, right? So, and then once we basically finish the execution of the interrupt service routine, it basically, that the close parentheses over there is going to call the return from interrupt, and that's going to actually return that instruction. This is just a high level. We haven't got into the details of, well, what registers are saved, how is it saved. So we can actually walk through that, right? So let's spend 5 minutes and actually look at what happens, when we are executing our user program, then an interrupt occurs, and then it has to go and service that interrupt handler, and then it can switch back to the user program. But it's not that simple of just switching over here. We have to see what's happening, whenever any of these interrupts are being called, that it's switching the control to whatever it is in the address of, where this interrupt service routine is implemented. And so essentially what what happens over here is that it's just going to say, well, if I have, like, let's say I have like a timer compare interrupt over here, B, right? So, and so in that location, it's going to essentially have the address of this interrupt service routine, and the compiler is going to say jump to that address. So the compiler is going to start to do some heavy lifting, and what we want to look at is, as we are executing these instructions and we have an interrupt, what is the compiler doing so that we actually jump to this address where this interrupt vector table is, look up the address of inside of that address over here, that suppose the interrupt vector is at, address 3E, 4C, and 3E, 4D, because every address is 2 bytes over here. And inside of that address, we have, the compiler has already placed the address of where this interrupt service routine is at 107B. So then we basically have to say jump to the address of 107B, and then go and execute that interrupt service routine, and then do a return from interrupt and come back to the next instruction over here. Now this next instruction could be 2 bytes later, could be 3 bytes later. That depends on the size of instruction M, and then that's where instruction N occurs. So let's actually take a step into what is this magic that this compiler is doing, and then walk through that, right? So we'll go through this example, and I'll show you what's happening here, right? So let's walk through these steps again. It's just a little bit of a repeat, but that I've written that over here. So when you reread the slides, you can see that, first the compiler finishes execution of the current instruction. Then it goes and clears the global interrupt enable,
When you say completes the execution, does that mean the instruction goes all the way through the pipeline?
Yeah, so in our case, we do not have a pipeline, right? So we do not have a pipeline-based processor. We do not have a superscalar processor. We are basically just executing in the instruction operand by operand, right? So operator, operand, and then we are completing that instruction. So we're just going through our fetch, decode, execution, all, byte by byte, like that, right? So to the high level answer to your question is yes. It has basically finished this fetch, decode, execute, cycle for that particular instruction. So say you're just adding 1 to the number in a register 7, then once it finishes adding that number and saves that number in register 7, then it says, okay, well, it goes and checks. It basically gets it gets woken up by the interrupt recognition hardware that we have an interrupt waiting for you, and then it knows that it cannot service the next instruction. It has to go and service the interrupt service routine after that point. But it needs to so there are two questions now, right? So who informed the CPU that there is an instruction, that is an interrupt waiting, and which interrupt is waiting? Okay, so that we're going to discuss after this part, right? So this part is just talking about in your code, you have written your code and you have an interrupt service routine, and you say, great, some magic is going to happen when I hit compile, that the program is going to know whenever an interrupt occurs, what to do, how to save its current state, how to go to that interrupt service routine. And so we are going to look at what is that magic. The second question is, okay, well, how did this interrupt actually come from, wherever it was, whether it was a timer interrupt or a pin interrupt? How did that interrupt actually percolate and find its way to the CPU? And how does it even know which interrupt actually occurred? Because there are so many different interrupts that could have happened. It's not going to just say, hey, you have an interrupt. How does it know which interrupt? Where should it go? So that is the interrupt recognition and service control hardware. We'll look at that after this part. Right
So
now,
if
yeah, go ahead.
If the instruction goes to completion before the interrupt instructions start executing, does it have to like stall then until the instruction is completed?
Exactly. It won't.
Why is that necessary if the way the pipeline works, it's supposed to appear as though it's happening sequentially anyway?
Because if you remember last lecture, we have to have some activity that is atomic. And if we even have an instruction that is divisible, then we can never have anything that's atomic over there. So a single instruction by definition is atomic because it has a lot of intermediate state that is in the circuitry that hasn't been saved into any memory location yet. And until we save our current work into a memory location, which is basically at the execute stage of the instruction, then until that point, we aren't able to checkpoint where we are in servicing that interrupt.
Well, they usually have like bypassing and stuff so that even if you have like saved memory and stuff, it still appears as though it's run sequentially, even though you have installed.
So the problem is that I do not know how to restart where I was in the middle of that instruction, right? So I've already loaded like a part of the instruction. I've started to compute now what is the A plus B, but that intermediate value of A plus B hasn't been stored back into any register. It has been computed by the ALU and it hasn't been committed yet. So it's kind of like you just
right. But that will eventually get to the execute stage, and that will be run before the interrupt instruction gets to those stages. So it will appear the same way. But I think the problem could be that the like status control register gets saved as part of the interrupt, and if that's not the same before as it is after that, maybe that's what the problem is.
So, but that's the status control register is one way of checkpointing that I have finished minimum, I finished the minimum unit of my work, and now I can go and do some other work. But the status register is one thing that has to be updated, right? But the instruction itself, if I have some intermediate computation in my ALU, that intermediate computation hasn't been stored in any location yet. So it is actually sitting in the circuit.
Right, but it's going to before any interrupt code starts happening because there's a pipeline.
I think we are trying to say the same thing in some sense, because if it's going to, then it actually has to, right? So it's not like it's going to happen in the background, because the program counter is then going to switch to the next instruction. So think about it like this. I'm in the middle of an instruction and I switch to another instruction. I haven't checkpointed like where I am in the middle of that instruction. And I haven't like, so I have loaded register 1, I've loaded register 2, or I'm in the middle of going and fetching some value from memory, and I'm in the middle of adding some value, and I haven't yet written that value back into the register. And then I'm just saying, no, I'm just going to go and execute some other instruction. When I come back, the ALU will still be holding that value. Or I'm fetching that value from the memory bus, and but I haven't saved that value from that is coming on the memory bus. I've just made a request to the memory bus, and I'm stopping right there. And when I come back, the memory bus will resume all automatically. But the memory bus, the registers, all of that have to be, they have to be ready for the next instruction. The entire system can only run one instruction at a time. It can't suspend an instruction in the middle of execution over there, because there's no way to know where I was in executing that instruction. Like I can't say I fetched the instruction.
It just seems like that's the point of the pipeline is you can be in the middle of instructions and queue up more instructions just using the program memory. So it's almost like you're just adding the interrupt program right after where the program counter is in program memory. So it's like you're just extending program memory, and it's just moving to the next instruction. And usually when it moves to the next instruction, it doesn't have to stall for the next instruction. There's bypassing and stages so that it still looks sequential, even though you don't have to stall and wait for the instruction to complete.
Yeah, so I think there is a little bit of mixing of concepts here, because in this microcontroller and in most microcontrollers, we do not have a pipeline. Okay, so this is not a pipeline based processor.
Right, but I thought we were talking about in general, like for a microcontroller that does have a pipeline.
Almost all microcontrollers don't have a pipeline. Processors have a pipeline, and the process that you are mentioning for a superscalar system that has a pipeline is very similar to what is called hyperthreading. Okay, so hyperthreading is in some way saying I can interleave instructions with each other, and I can even execute, instructions concurrently. Like while you're going and fetching something, and it's going to take some time, you can execute some other instruction that is independent of this instruction like that. So that's in some way, increasing the throughput of the system. So now, or being able to checkpoint where you are in a pipeline. So I think the question you're asking is, for a system with a pipeline, if you know where you are in the pipeline, can you basically just save what is in the pipeline and then go ahead and execute another instruction and then come back and load the pipeline back again?
I'm just saying, wouldn't you just be able to stick the interrupt instruction into the front of your pipeline, and it would just go through like normal without having to wait for all the instructions that are currently in the pipeline to finish before you put the new interrupt instruction in? Since it's a pipeline, you should just be able to stick it in the queue to go into the pipeline without having to do extra stalls and wait for everything to execute all the way.
So what is a pipeline? Right? A pipeline is executing one instruction after another, and the first instruction, say for example, hasn't completed yet, but you've started the second instruction in the fetch, decode, execute sort of stages, right? So while the first instruction is in, say, the execute stage, the second instruction is in the decode stage, the third instruction is in the fetch stage, and they basically are going through this pipeline, right? So therefore you can think of a pipeline as a multiple stage buffer, right? Or a queue, and you're putting instructions through that queue. in the microcontroller, the queue length is only 1. So you're doing fetch, decode, execute, and you can only do that for 1 instruction at a time.
Yeah.
There
So
is no queue.
that makes sense that you would have to wait till completion if there's no like pipeline with multiple stages in a microcontroller. That makes sense to me. I think that's just what our confusion was then.
Yeah, there is no pipeline here.
Okay.
So yeah, if you do have a pipeline, then yes, it'll. So say like your pipeline depth is 20 instructions, right? So when this interrupt happens, the question is, does the interrupt get to the top of the pipeline where it is the 21st instruction and it has, or does it actually get into the end of the pipeline where it is just pausing the current execution of the current instruction and then just going to that out, right? So that's a question for, depending on the architecture. The architecture will sort of have 2 kinds of interrupts, okay, and that we can cover that too in the as a follow-on question, and I'll just type that in the list of questions here. So there are interrupts versus fast interrupts, and that's another way of speeding up, the latency or lowering the latency to servicing an interrupt. And so we'll look at that too. But that's a good question, right? So, why do we have to wait for completing the current instruction? So you should be able to answer that because, we haven't committed our work yet, right? So it's kind of like you're using GitHub and you're doing your code and you're saying, okay, I'm going to commit my code every 5 minutes. And at 3 minutes, you get a call and says, okay, whatever, coronavirus hitting campus, abandoned campus. And you're like, well, the next commit I have is at 5 minutes. And so now you're not yet committed, you're not backed up your code yet, right? So you have to figure out how to back up your code. You have to wait for 2 more minutes till you finish, or in that example, you don't have to wait. You can just commit your code at any arbitrary point, even if there are errors in your code. But for the instruction, it has to complete till it is done with the execution stage of the full instruction, right? So then as soon as the interrupt occurs, it finishes the current instruction, then it clears the global interrupt bit. Basically, it's disabling any more interrupts from happening, right? And then it saves the current program counter on the stack. Then the interrupt vector is triggered and loaded into the program counter, right? So the interrupt vector of the triggered interrupt, so it needs to know, okay, who interrupted me, and then it says, okay, then jump to that interrupt's address, look at the address in that interrupt vector table to find the interrupt service routine and load that to the, then get the PC to then jump to that address, right? So
can I ask a quick question?
Yeah.
To point 2, do the other interrupts just get ignored now, or do they get queued?
Good question. So the short answer is for this microcontroller, only 1 interrupt can be serviced at a time. And when we look at the interrupt recognition and control hardware, you'll see that it can buffer the fact that there was another interrupt, but it's not going to be servicing that other interrupt. Now, just like Matt was talking about a pipeline, you could have processors would have a pipeline that make a queue of all the interrupts that are occurring while you're servicing an interrupt. Now, we can cover this a little bit later to the latter part of today's lecture is, this nested interrupts, right? That while I'm executing an interrupt, can I still A, keep registering and just queue up other interrupts, B, get interrupted while I'm within an interrupt service routine. So I'm servicing interrupt 1, the first interrupt, and then in the middle of servicing the first interrupt, I can get into a nested interrupt in that point, right? And so we'll look at that. That's also part of this lecture. And but these are great questions. I think what it really means is that we should just go through this example, go through the hardware, and then there is a portion that talks about these nested interrupts and fast interrupts. So let's do those three things, and then we'll get through. But ask questions along the way, right? These are good questions. So we save the program counter on the stack. That's for the main program. Then we go and look up in this interrupt vector table, where is the location of my interrupt service routine, and then set the program counter to that, right? Then the microcontroller basically starts execution of that interrupt service routine till the point of this return from interrupt instruction is there. That's the end of that interrupt service routine. When it executes this return from interrupt, what it's basically doing is that it's going to look at the stack and seeing what is the return address, and then it basically goes and re-enables global interrupts again in the in the status register, and it's basically saying, okay, now we can service more interrupts, and then it returns to the interrupted program by looking up the return address, and then it starts executing the next instruction. If there is another interrupt waiting, then it'll again go back through this whole thing and save on the stack the same stuff again, right? It's basically popping off everything of the stack, then it is pushing back everything on the stack and then servicing the next interrupt. So let's look at that. It sounds a little bit wasteful if we have back-to-back interrupts, and that's where these fast interrupts come in play over here, right? So we'll look at that too. So let's say you wrote some simple code over here, right? So you have your main function, and then you have this timer interrupt over here. Can you guys see my mouse over here? Just say yes or no.
Yes.
Okay, good. So essentially, we are in this location. We have some simple timer interrupt that says, okay, well, whenever this timer happens, I just set capture to be equal to 1. Okay, so I'm just enabling my timer over here, enabling global interrupts, and then I'm just have a while loop over here and saying while it's not captured, then I haven't, like, say I'm waiting for a rising edge, like that, right? So if I'm waiting for a rising edge, whenever I get the rising edge, it goes to that, it writes capture equals 1, and then I just say, hey, I captured an edge, great, and then I just clear that, and then I'm just again waiting for the next rising edge, right? That's it. So it's a really simple program. And so now we want to sort of look at, well, this main interrupt service routine here is just doing one line of code, right? So it's just writing a 1 to this global variable capture, which is just a global variable. It's a volatile int capture equals 0, right? So it is a 2-byte value over there. It's an int. So let's see what happens when we actually compile this code and we have our we have our interrupts. We are just looking at the interrupt service routine, right? So when you compile the code, you would think, hey, it should just be writing a 1 to capture and that's it. But what the compiler does is that it actually adds a prologue in your main code, and then you have your body, which is actually what it is actually doing. And then it has an epilogue. So the prologue is all about what should I do before I get to this interrupt service routine. And then the epilogue is, okay, what should I do when I'm done with this service routine, when I'm doing, and that's basically when this close parenthesis is over here, that's just saying I want to return from my interrupt, right? So it's essentially the compiler has some code for, loading all the saved registers it has used so far, right? So let's look at what happens in this prologue over here. So it's just essentially saving, the current registers that are on the stack. So say the compiler so far in this program has only used register 0 and register 1, and it does not have to save all the registers. Now, how does it know which registers it has used? Because the compiler is actually deciding which registers are going to be used at any time in the program. It is keeping a stock of which are the dirty registers. Dirty registers just means the ones that are being used, right? So so it essentially just pushes R1 on the stack, pushes R0 on the stack, and then it loads the status register into R0, and then it pushes R0 onto the stack. Now you might say, why does it have to do it in 2 steps? Because it can only push stuff that are in registers onto the stack, but the status register is a special register. It can't push that directly onto the stack. So it has
Since
to load
interrupts,
it to a general purpose register and then push that on the stack.
Interrupts can happen at any time, doesn't it?
which registers you would push to the stack change like dynamically?
No, no, they won't change dynamically. They would. Let me just think about that, because so the compiler knows that up to this point in the code, right? So like within let me say, like within the scope of a function, right? So within the scope of the main function, these are the registers that have been used. And it could be that, you know, the code gets interrupted before, like, you know, register 7 and 9 have been used, but then it still saves those. So it just knows that in the scope of this function, these are the registers that are actively used. And if I get an interrupt early in that code and I haven't actually used register 7 and 8, then it still saves that, right? So it is at the function scope level, it knows which register to use it, because it does not know, like at this point, you know, which registers have been used. It's just saying,
What if you're in a different function though?
if I'm in a different function, so at any point, okay, so at any point, then it knows, okay, I see what you're saying. If I get interrupted at a different point in the code, right?
Yes.
Okay, that's a good question. So if I'm, because I could have function 1, function 2, function 3, and I could get interrupted at any point. But where are those functions being called from, right? They're being called from the main program, right? So in this case, since our program here is a really simple program where I only have a main program, I don't have other functions over here. The compiler is just going to look at in the main program scope, right? So when can an interrupt me? It can interrupt me at any point in the main program scope over here. And so since I don't have any other functions and it's only using R0 and R1, then it just saves those two. Now, if I have a main program that is more complicated, that calls other functions, then in that case, it's just going to save all the active registers that are being used. Now the compiler, that would be the naive approach, right? But the compiler would have some way, because the compiler is running in a non-runtime manner, right? So I think that's the core of your question, is the compiler has no sense of what is happening at runtime. And the compiler has no sense of when this interrupt can happen. So the compiler has to basically just save all the active registers that are within that scope of that function. So if that function is using, you know, all different registers, then it will save all of those.
Okay.
So yeah, there could be ways, and I'm sure there are ways in which the compiler can optimize, you know, instead of saving all the registers, just save a subset of the registers that have been recently or used within the scope of just that function, right? So but the thing is that the compiler, when it writes this code, right, this code is basically part of your image now. And so this image over here is done at compile time, right, at design time over here. So
Could it possibly use the program counter and then like write an if statement to say which registers to push?
Yeah, in some sense, I would say that's more on the side of like a compiler optimization. And there would be some much smarter ways to actually reduce what is pushed onto the stack. Because in like modern processors, I mean, even in this microcontroller, if you have a lot more code and you're going to be using all 32 registers, and at different points in the code, it's going to be saving, you know, all 32 registers then, right? So in that sense, a second kind of observation that you're touching upon is that, you know, if you have code that is using a lot of registers, then your interrupt latency will also go up. In this case, the interrupt latency is lower because to service the interrupt, I'm basically just backing up. I'm only pushing R0, R1. I always save the status register. So I don't want to. So I'm sure there are compiler optimizations that can sort of look at, where in the code, depending on where in the code you are, they can say, well, these are the active registers at this point, right? And they could maintain a list of active registers. So one way I would do it without knowing, what are different compiler optimizations that are out there now, is that at this point in this code over here, I would say that these are the number of active registers, and I would have like some kind of checkpointing in that sense, right? But that would be much more advanced in terms of optimization. Let's learn the vanilla version, and then we can sort of discuss how optimizations work, because then that allows us to at least finish learning, well, how does a basic interrupt actually get serviced? And then all these, exotic, I would just call them exotic questions of, or more advanced questions of, can we optimize this? Can we optimize that? We can look into that right after this. So now we save basically our registers, our status registers, then we clear basically the registers. So this is just an assembly macro that is just saying, clear the registers, which are like clear the active registers, which is basically just resetting, R1 to 0, and then it's basically pushing, the R24, R25, and that's where we are storing this capture variable, right? So now we are at the main program, and we are getting interrupted in this for loop essentially. And in this for loop, we have one global variable, and that is basically capture over here, right? And so we are going to save that capture variable over here also onto the stack. And but that's a global variable now, 24, 25. And so now we are putting everything onto the stack, and in that order, right, of R1, R0, status register, and then any global variables that we have. And then this is the body of our code. Essentially, the body of our code is just writing a 1 to this capture variable over here. And what it's actually doing is that it is loading it directly into this register R24, R25, and it is just writing a 1 to R24, which is the lower byte. It's just called the lower 8. Don't worry about all of this stuff over here, right? This is just some kind of very processor specific jargon over here, but all it's doing is it's just saying write a 1 to register 24, write a 0 to register 25, and all it's doing is it's just storing, like, these that register back, right? So it's just saving that value of this global register, of this global value, to capture now, right? So it's writing essentially a 2-byte value where the lower byte is 1, the higher byte is 0, and that's the bottom half is and it's saving the bottom half into R24 because it's a 2-byte int is a 2-byte value, and then it is storing that value over here of the upper byte, which is R25, and then the lower byte into capture. And you might say, well, what is capture? That's the location of the globe in RAM for the global memory. Now, I just want to make sure, like when I was, had this code for the first time, I was confused that, wait a minute. So we are using R24, R25 here, and this is in the body of our interrupt service routine, right? So yeah, sure, we can use R24, R25 because it has already been pushed over here, right? So but that's just the local register value for R24, R25, and that was the old value of capture. Now we updated the value of capture in this status register, and we saved it in the global location of where capture is. So we are not going to resave it again when we get back into our main code. We are basically writing to this global location that capture, the variable capture has now been updated to have a 1 in that location, right? And then when we get to, we are basically now getting to, we are finishing up our, we've finished writing our main one line of our interrupt service routine, and then now we're going to basically pop back everything from the main program. So pop R25, pop R24, R0, status register, R0, R1, all of that stuff, right? And save that into the status register and then come back and then say return from interrupt. And that's essentially going to basically go to the stack and load the program counter from the stack. And it's going to transfer the code back to the main program over here. And that's essentially what's done over here. So questions. There are some things that are a little bit confusing over here, but let's have some questions regarding this code. And essentially this code is all here, right? So all this code just belongs to after, like, just when I'm starting to service the interrupt, I go ahead and service the interrupt, and then I'm done servicing the interrupt and I'm coming back to the main program. So actually my main body is just this. It's just basically updating the capture value. But I have this prologue and this epilogue to maintain the state of the main program. Anything not clear in this example?
How does the first instruction get queued of the interrupt code?
What is the first instruction?
Like push R1. Sorry, not push R1, but the jump.
Oh, so when you actually call the jump, you mean? So
Yeah.
So when if we go back to this case over here, where this instruction of going to that location, right? So that is getting queued now. That's a good question. That is getting queued by the CPU is essentially getting triggered to say that you have an interrupt, and here is the interrupt address, and you need to go to that address, right? So that jump over there is being called by the hardware of the microcontroller to service that interrupt. So let's look at that hardware now. If you don't have any other questions with this code, then I'll address that question. Anything that you're not clear about in this code? Any one of you all? It looks okay so far? Okay, so yeah, it's not rocket science, but yeah. So what I got confused about when I was reading this for the first time is, okay, so I saved this capture over here as part of R24, R25, and then I'm essentially also saving capture to this main location. And if I go back to my C code, then I essentially, if I got interrupted somewhere here or here or here, this capture value was my old value, which I had saved before I got interrupted, and that value was 0. When I got interrupted, that value became 1. Now, do I use that value in the main program, or do I go and so why did I have to save that global variable value when I'm actually in the body of the of the interrupt service routine? I'm actually going and updating the value directly in RAM, right, of where that global variable is. That's just because whenever we are just saving all the variables, whether they are local or global, in the prologue, and because those registers were deemed dirty registers. And so is it, when we come back to the main program, it's not really using that value of 24, 25. It's just going to be it's going to actually go and look up the value from RAM of what the value of capture is when it is executing this line of code over here. Is capture 0 or 1, and then it's actually just looking that up. Okay, so if there are no more questions here, then let's look at what happens. Yeah, so this is just saying that this is compiler generated overhead. This is your code, compiler generated overhead. And so can you, and that basically introduces some interrupt latency also. And so we have this time over here of, saving the stack, going to jump to that location. Then we service the interrupt. Then we again have to sort of pop the stack and then get back into the program. So now if you want to do that, then that is going to take several instructions, right? And so that is the overhead of servicing that interrupt over there. And so when an interrupt happens, all the interrupts basically go into this interrupt controller unit over here. And then this interrupt controller unit goes and sends a flag over the main bus. And so this is also like a peripheral, right? Like a peripheral, like a PWM or a ADC that's connected to the main bus. And it sends this signal, it sends this message to the main CPU that, look, you have an interrupt and it's waiting for you, right? But let's zoom into that and let's see, how do we actually determine, okay, there is an interrupt that has happened, and how do we know what is the source of that interrupt, right? So we want to essentially go and look into this hardware, right? So essentially this interrupting device, right? And that could be any of these interrupts, a timer, or it could be a pin interrupt, it could be a watchdog timer, whatever, any of those. They basically are the interrupting device over here. And we do not know yet which device it is. It is just that we are getting an interrupt into this interrupt, controller. And then that interrupt over here, it is a analog signal that is coming in to the circuit. So there is some signal conditioning, and we have to do some sort of, noise limiting, and just basically convert that to a digital signal coming in. So the rest of the circuit can be a digital signal, because then we set that as and we save that in a buffer, which is a IRQ flip-flop. And that's just a set reset flip-flop over here. And a flip-flop is just storing a value. And so we're just setting that value. And then once that value is set, we have that saved in this buffer. And if global interrupts are also enabled, then that basically goes into the sequence controller and says, hey, you have an interrupt over here. Now the sequence controller says, okay, I have an interrupt. The sequence controller has to go and look up what is this interrupt that is there. But while it is, looking up that interrupt, and it basically says, okay, no more interrupts are allowed. So it basically goes and disables, the interrupts after this point, right? So you can disable the interrupt by actually writing the status register interrupt I to be 0. But this in sequence controller is doing that automatically, right? It's going and disabling, any further interrupts from coming through till it has actually serviced this interrupt, right? So, and what does it mean by servicing this interrupt is that it has identified what is the type of interrupt, and it has informed the CPU that, this is an interrupt that is waiting for you, right? So essentially it goes and disables now, it goes and disables the interrupt flip-flop, interrupt enable flip-flop over here, so that the next interrupt that comes in is not able to come, is not registered over here yet, right? So once we actually have determined, well, what is the interrupt that we have, and then the sequence controller basically goes and does a reset to this flip-flop. And so if global interrupts are at this point, we have started to go and service that interrupt, but it has handed that off to the CPU to go and service that interrupt, move the program counter and that code that we just saw. And so at this point, another interrupt can come in, and it can just get registered that there is another interrupt waiting. But we are not going to process that other interrupt because it is waiting here, but global interrupts, the interrupt enable over here has been disabled. So it hasn't progressed to this stage. So the first interrupt comes in and there's no other interrupt. it passes through, and now we're going to look up, where this interrupt happened. And once we know where this interrupt happened and we inform the CPU, then we send an acknowledgement back over here. And that allows the second follow-on interrupt to come in and just wait over there. We haven't sort of decoded it yet. Okay, so now let's look at, so we have two flip-flops here. There's a IRQ flip-flop that basically just generates that there is a pending interrupt, and it's just basically putting that in a queue, and the queue is only one, right? So you can be servicing one interrupt, and you can just buffer the next interrupt, but we can't be servicing more than one interrupt at a time. And then we have this interrupt enable flip-flop over here that basically is reset when the CPU acknowledges that the interrupt is just this global interrupt signal is set to 1 again, and then it allows the next interrupt to pass through. So let's look at what happens once the first interrupt comes through this pipeline. Global interrupts are enabled. We have a pending interrupt, and we want to service that interrupt, right? So we need to figure out.
Real quick, what happens if you have a pending interrupt and your interrupts are disabled, and then you enable the interrupts? Does it ignore the current pending interrupt?
No, then it allows that. So that pending interrupts, that signal is here, right, on this line.
Right.
As soon as you enable this, then it allows that.
Say I press a button and it triggers an interrupt, but I have interrupts disabled, and then 2 seconds later I enable interrupts. Am I going to detect a button press?
You are going to detect a button press. So many times when I start my laptop, I just type in my password really fast, but it doesn't appear on the screen, right? It is actually getting stored as a sequence of interrupts that have happened, and those values are being written to some buffer, but the screen hasn't been updated yet, right? So it's almost like it has a sequence of pending interrupts that are there, but they haven't been processed yet. But once the CPU is able to process them, it says, okay, well, I have a queue of interrupts that I need to service, and then those dots start to appear or on the screen, right? So sometimes you just open like a new document and then you start typing and nothing comes up on the screen, and that's exactly what's happening over there. That it's just saying, I have registered your interrupts, and so it knows I pressed the button like R, A, H, and then it knows that, right? So but it hasn't been able to service that yet. It just knows that there is an interrupt. So let's look at what happens now. So this is just the text of what we spoke about. But so when an interrupt actually happens, we need to go and check, what was the source of that interrupt, right? So there are a couple of ways to go and look that up, right? So we can look at it in software where the CPU can go and say, okay, well, I got an interrupt. Then the CPU can go and poll the status registers of all the devices that have these interrupts and check, like, do you have an interrupt for me? Do you have an interrupt for me? And you can do that in software. And obviously that's not the most efficient way of doing it. Or you can do this in a hardware where you actually now say, okay, I have generated an interrupt, and then it basically goes the peripheral that has sent that interrupt, basically that writes to this bus that talks to the CPU, and the CPU basically is requesting and asking all these peripherals who sent that interrupt, and then the peripheral will respond and it'll say, okay, well, I sent that interrupt. Now this is not done as part of your code, right? This is done as part of the implementation of the interaction between the CPU and the interrupt control unit over here, right? So the CPU is, once it has been informed that there is an interrupt, it has to go and check, who is the source of that interrupt, right, over here. So you can do that, and like what is written over here, you can do that in terms of that you could actually have like some firmware that is going and checking up the interrupts over here. And or you could actually have this as part of some hardware where you sort of look at the logic and say, okay, well, logic to read the status register and basically check, okay, to generate the IRQ, and then it's basically saying, okay, well, who has generated that signal? It's polling that, and then the peripheral that has done it basically sends a message and says, okay, I have done it, and it is giving its its ID over there, right? So that's
So if
one way of decoding like which interrupt happened. Now, this is a little bit abstract over here because this is actually very much under the hood in terms of how the logic of looking up an interrupt from a table of peripherals that are there, and generally this is the one on the right hand. That's the hardware based method of actually looking up and just checking the status register. So what the CPU would be doing then is actually would just be, in hardware, going and scanning the status register of each of the peripherals and just looking at which one is set. And or alternatively, the peripherals themselves could be responding and with the value as they are queried. What's your status register? What's your status register? So this is not happening as part of your code now. This is happening at a much internally to actually look up that, right? So
if
now,
it's happening in software, would it just go in your Prolog?
If it's happening in software, then it depends, right? So it depends on, are you using an operating system or not? If you're using an operating system, then the epilogue, in this case, in the case of our code over here, in the Prolog, it would basically say, call this kernel function that is going to discriminate and identify which interrupt actually happened over here. And that would be quite inefficient, but that would happen in the case of where the question was, what if I implement my own interrupt? If I have a user-based custom interrupt, in that case, that would be the best way to do that. But in general, your hardware is going to be looking up the interrupts that you have and checking which peripheral actually has a flag that is high, and that peripheral has been cleared to say that I have that was my interrupt.
Is the bullet point on the slide wrong then, because it says that software is responsible for finding this interrupting source?
That's in this case over here, right? So
okay.
Yeah. So that's this is just saying that this is a software based approach. The hardware based approach is over here, right? So the hardware based, so this is so sorry, I think I'm confusing you a little bit. What is in this purple box over here? This is sort of just zoomed in, and the software is doing these processes over here, right? It's basically having this conversation, versus you could just have all of this as this, instead of having a software based conversation, you would just have this logic that does this lookup, and then each each of the peripherals would say, okay, I have received a query for, is it my interrupt? If it's my interrupt, then it basically writes that to the bus and replies that yes, that was me, right? So it is identifying that. So the CPU's response is to assert an interrupt acknowledgement, and so then basically that is just saying, okay, well, the interrupt acknowledgement is like an internal instruction that is sent on the bus to that the interrupt controller will then register, will check and say, okay, well, we need to respond with which peripheral. Each peripheral will receive that interrupt acknowledgement and say, okay, the CPU is now acknowledging that it's going to service that interrupt, but we need to say that you need to raise your hand, and this raise your hand is done in hardware in this case. So the the vector information is just the list of all the interrupts that are there, and that are and the flags of which interrupts were activated at that point in time. So this is happening internally, right? This is not something that you see in your code. This is not something that is running as part of, assembly or anything. That is this interaction between the CPU and the interrupt controller, and between the CPU and the peripherals that are there. The interrupt controller is storing the information of what is the status of each of the peripherals. And so when the CPU is acknowledging that and saying, okay, I'm ready to service interrupt, then it says, okay, who interrupted? And then this could reside now in, either in the peripheral, or it could reside in the interrupt controller to say, okay, well, I'm the responsible party, and it acknowledges that. So the thing is, you can have multiple interrupts and you want to mask certain interrupts. Yeah. So there was a question like, can I mask an interrupt? So you can mask interrupts, and you have two types of interrupts that are there. You have maskable and non-maskable interrupts. And so this is just talking about, can you have nested interrupts? Yeah, you can have nested interrupts, but not in our microcontroller. And but most processors, they allow for nested interrupts. And the thing that I want to talk about now is just this last question of, what happens when I want to mask interrupts, right? So I can basically mask an interrupt by saying, well, in order to enable an interrupt, I have to enable that particular peripherals interrupt, like a ADC interrupt, and I also have to enable global interrupts, right? If I disable global interrupts, then I'm disabling everything. But I can disable, like, a particular peripherals interrupt, and that's one way to do so. So in most processors, you will have an interrupt mask, and you've actually enabled that, right? These timer masks, or TMSK1, or any sort of mask register, just saying, well, which interrupts are enabled, which interrupts are disabled. So you can actually disable in certain interrupts. Certain interrupts now are, due to faults and due to resets. Like if you have an illegal instruction, or if you have like a divide by zero, or if there is like a overheating of the CPU, then the CPU basically has to send a message out and say, we are shutting down now, right? And that has to go and basically call the shutdown sequence and power off, or it has to reset the CPU for some reason. So all of those are, essentially non-maskable interrupts. And so that's just for the safety and the protection of the CPU. But you can program what happened, like how the CPU should deal with certain things, right? Suppose there's a divide by zero, you don't want the CPU to just reset. You can actually go and program that in the BIOS, or when you set the fuses. When you're programming the microcontroller, you can set the fuses, which are special memory locations that say, how should this microcontroller behave if there is a divide by zero? How should this microcontroller behave if there is an illegal instruction, right? So that means there is AGXY, for example. There's no instruction like AGXY. And then if it gets that instruction because a compiler introduced that, or the code, there was some garbage, injected into the code, then it should be able to deal with that gracefully. And, and so it shouldn't just like, try to execute some random instruction, or shouldn't just cop out and, just get reset. So you can set that as part of, how the microcontroller behaves as part of that. Okay, so we are out of time for this lecture, but this particular slide deck is for 2 lectures. So we can continue, like the questions on what does the watchdog do, how do we deal with interrupts and concurrency in the following lecture. So any other questions so far? So what are things that we can cover? So we'll cover the watchdog timer. That's actually very important whenever you implement some safety critical system. The other thing that we skipped over was reentrant functions. That's another question, if you have questions regarding that. And then this is a very important problem over here, is that, you know, if you have an if you have an interrupt service routine, and you have to do a lot of work whenever an interrupt happens, like say I press the command, I press the keyboard button B, and that launches, like, you know, like a some like a web browser app, right? So but for Chrome to launch, it basically is going to take like thousands and thousands of instructions. I don't want to have my interrupt service routine, you know, be running thousands of instructions. So how do I split the processing between saying, okay, I got an interrupt that you pressed the button B, but I want to be able to launch Chrome outside of the interrupt handler. So how do I split that processing of, you know, capturing the actual signal that the interrupt is sending, and then doing the work, you know? So how do I execute things quickly and then perform, you know, like a large amount of work, but I don't want to perform that large amount of work in the interrupt handler. So that's another aspect that is really important to understand. And if you have questions regarding that, let me know. And the last thing is also of, you know, external interrupts, but that's pretty straightforward. You can look at that, and there's also a video that we can walk through in the next time. Okay, so before we wrap up, any questions? Did you find this useful, the lecture so far, or the question and answer, the lecture? Okay, so okay, so any last questions? I like that ENIAC background you have.
Thank you.
Okay, any last questions? So we'll continue these and come with more questions in the next lecture, and then we'll cover more of interrupts at that point over there. Okay. All right, guys. Have a good weekend. Don't party too hard. Okay.
Thank you.
Thanks, Rahul.
All right. Bye.